A statement from Stephen peddling the consistent state hypothesis was what Karl Popper would call a great logical hypothesis. It made unambiguous expectations that could be affirmed or refuted by perception. Sadly, it was negated. Cambridge teachers Fred Hoyle, Herman Bondi, and Thomas Gold unexpectedly acknowledged later at an unusual film night that the universe should be everlasting. The new hypothesis has had an impact on the manner in which we contemplate the universe. Everlasting matter replaces matter. There is no such thing as time, and the universe is in an everlasting, perpetual state. If Hoyle, Bondi, and Gold are at that moment, shouldn't something be said about the huge explosion? More critically, what film roused the three so much that they concocted one of the most discussed hypotheses of the 20th century? What are 330-something Cambridge space science and astronomy instructors doing on a Saturday night? No, they're not discussing heavenly masses or cosmic nebulae. They're watching a horror flick. It was 1945, and Dead of Night was the film. The English horror movie consists of several interconnected short stories embedded in a fascinating frame story. Dead of Night starts with an architect named Walter Craig, who is invited to a remote ranch-style home. There, he meets a group he doesn't really know, but individuals appear unusually familiar to him. Each one recounts a spooky story they had experienced. The stories all include otherworldly events, such as ghostly phantoms, a shocking mirror, a cursed golfer, and a dreadful ventriloquist dummy. The frame story connects these accounts and ends with an astounding twist. Walter Craig realizes why he somehow knows all this. He understands that he has encountered these stories before in his dreams. He realizes that the entire event, the meeting at the ranch-style home and the recounting of the stories, is part of a recurring dream. When he realizes this, it turns out that all the creepy events and experiences didn't occur in actuality. The end of the film shows Craig awakening from the dream, and reality presenting itself as normal again. Still, it remains a fascinating story because the film explains how dreams and reality can blur together. Just as the audience couldn't tell whether they were experiencing something real or just an item of their imagination, the same could happen to us. The plot of the film also leaves open whether the events in the ranch-style home actually represent another level of reality. So what did this film trigger in the three teachers from Cambridge? After watching the film, each of the three men independently had the strange feeling that there was more truth in the film than they thought. They had spontaneous dreams of an endless universe, and everything seemed absolutely plausible to them. In the months that followed, they developed a model to explain the universe that we now know as the steady-state hypothesis. The steady-state hypothesis describes a universe without change. It sounds insane that a horror film inspired three top researchers to come up with one of the most examined hypotheses of the 20th century. After encountering the film, the fact that older speculations were right, according to which the universe is maintained by a continuous stream of matter and that our universe may not be the only one. Such thoughts arose as early as 1918 when the American physicist William McMillan suggested that new matter is continually being created within the universe and that the universe is thus maintained in a steady state. In the 1920s, James Jeans proposed that this matter is made in twisting nebulae and really comes from other universes. Even Albert Einstein briefly took up the idea, publishing a paper in 1931 in which he described the idea that the universe expands through a continually growing stream of matter. However, physics then developed in a different direction due to the work of Hubble and Lemaitre. The concept of the Big Bang and expansion in existence became established. In 1948, Fred Hoyle, Herman Bondi, and Thomas Gold proposed what is likely the most robust counterhypothesis to the Big Bang model, the steady-state universe. This hypothesis states that the universe has neither a beginning nor an end and that new matter is created continually. The expansion could thus be an optical illusion triggered by the influx of matter. As we know today, excess matter is sucked out of the universe by black holes, for example, and potentially channeled back into other universes where it is restored. During the 1950s and 60s, the steady-state hypothesis was discussed by many researchers and, for a time, competed with the theory of cosmic detonation for dominance in cosmology. Has the hypothesis truly been negated? We should take up the statement from Stephen. He said that the steady-state hypothesis was Karl Popper's idea of a good scientific hypothesis. It made unambiguous expectations that could be affirmed or refuted by perception. Sadly, it was refuted. Hawkins saw the hypothesis as refuted. This was due to observations made by researchers from the 1960s onwards. Yet, before we turn our attention to these discoveries, we should investigate who Karl Popper referenced in the statement. Popper was an Austrian-Hungarian philosopher and mathematician, and one of the great scholars of the 20th century. He said accurately that scientific theories can never be conclusively proven, only disproved. In plain language, this means that scientific theories remain theories until they are replaced by insights or are refuted. Then there is a counter-hypothesis that tries to prove something different. However, they remain hypotheses. This is precisely the issue our science is currently facing. The house of cards of its hypotheses is collapsing due to actual observations. The issue is still that the observations are far from giving us the truth. Only when all the hypotheses fit together consistently, complement one another harmoniously, and lead to what Albert Einstein called the unified field theory can we accept that we have found the truth regarding the universe. Anyway, back to our three film fans and their steady-state hypothesis. During the 1960s, the steady-state hypothesis was apparently discredited by several observations. Radioastronomical discoveries showed a higher number of radio sources and quasars at greater distances, suggesting that the universe is not static but changing. In 1965, Arno Penzias and Robert Wilson discovered the cosmic microwave background radiation, which has since been recognized as a remnant of the Big Bang. This discovery provided solid evidence in favor of the Big Bang hypothesis and contradicted the assumption of the steady-state hypothesis that the universe has no temporal evolution. However, nothing was conclusively proven. It was just that there were strong theories contending against the steady-state idea. If we look at the concept of a temporary and spatially infinite universe, this idea does not necessarily mean that there are no developments, changes, and dynamics within this universe. The hypothesis only states that the space in which this happens is infinite in a specific way. You could think of it as a lake into which water flows with elements and life within it, but the lake itself is everlasting, an aspect beyond time and space. The idea is crazy that we might have gotten ourselves tangled up in an issue due to a small mistake in perception. Some scientific theories propose that time and space are illusions that lead to false scientific assumptions. Yet how could this be? Our senses and measuring instruments are designed to perceive and measure existence. However, if these aspects are indeed infinite, our perceptions and the theories derived from them could be deceiving. This means that many scientific assumptions made based on reality might be mistaken. We are at a delicate edge in science. The James Webb Space Telescope is an $11 billion project designed to show us the first galaxies of the universe. However, what do we see? Lines and lines of galaxies that are so highly developed and structures so massive that they could not have existed in a universe that was only 200 to 300 million years old. Even a few scientists are already willing to say it outright and admit it. These discoveries suggest that the universe is far older than previously thought, or that endless science is often reluctant to move on. Many researchers have become too enamored with their old theories to abandon them now. It almost seems as though a group of elderly men are stubbornly defending theories like the Big Bang and expansion simply because they are afraid that everything they have believed in for their entire lives is wrong. However, there are also other young and open-minded scientists who will welcome all new discoveries with interest and openness. After all, science is not about being right but about the truth. Consider the possibility that the steady-state hypothesis is correct after all. What scarcely anyone knows right now is that the cosmic microwave background has also long been questioned, not its existence but its origin and meaning. Some viewed the cosmic background radiation as a development that began from a single point. However, specialists have even found evidence of parallel universes in the radiation, and Sir Roger Penrose used the patterns in the radiation to support a recurring universe. This shows that radiation provides space for numerous interpretations and perspectives. The radiation could also relate to the ongoing stream of matter, and this stream could, in turn, explain why the universe appears increasingly inhomogeneous on a large scale, which shouldn't be the case if new matter is continually being created. This could help explain anomalies in the distribution of matter in the universe. This inhomogeneity is one of the greatest mysteries of current research. If the Big Bang hypothesis is correct, the universe should be uniform, homogeneous, and isotropic. However, the Webb telescope shows us that this is not accurate. Some advanced theories of quantum gravity, like loop quantum gravity, suggest that space and time could be quantized. Quanta are known to exist in different places and at different times simultaneously, as they are the building blocks. To extend the discussion on the steady-state hypothesis and its place in modern cosmology, we should delve deeper into the reasons why the hypothesis has sparked both significant interest and controversy over the decades. The steady-state hypothesis, while initially competing robustly with the Big Bang theory, eventually faced significant challenges that led to its decline in favor of alternative explanations. One key aspect to consider is the observational evidence that accumulated over the years. The discovery of the cosmic microwave background radiation in 1965 was a watershed moment. This radiation is often described as the afterglow of the Big Bang and provides strong support for the model of an expanding universe. The uniformity and isotropy of this radiation across the sky suggest that the universe underwent a hot, dense state in its early moments, which is a cornerstone of the Big Bang theory. Another major development was the observation of distant galaxies and their redshifts. Edwin Hubble's initial observations in the 1920s showed that galaxies are moving away from us, with more distant galaxies receding faster, indicating that the universe is expanding. This observation was one of the first empirical supports for the Big Bang theory. The steady-state model struggled to explain these observations because it posited a static universe where matter is continuously created to maintain a constant density despite the expansion. The steady-state theory also had to contend with the discovery of quasars, which are extremely energetic and distant objects. Quasars emit vast amounts of energy and are observed at great distances, implying that they existed when the universe was much younger. This challenges the steady-state model's assumption of a uniform and unchanging universe because it suggests significant changes in the universe's structure and activity over time. Furthermore, the theory faced criticism from theoretical physicists. For instance, the steady-state hypothesis required a mechanism for the continuous creation of matter. While the theory suggested that new matter is created in the form of hydrogen atoms, this was not sufficiently detailed or supported by empirical evidence. The theory needed a mechanism that could be observed and measured, which it lacked compared to the well-developed Big Bang theory that provided a more comprehensive framework supported by a range of observations. In addition, the steady-state theory's assumptions about the universe's uniformity and lack of evolution were increasingly challenged by observations of large-scale structures in the universe. The discovery of the large-scale structure of the universe, including the distribution of galaxies and galaxy clusters, suggested that the universe's structure evolved over time. These observations were inconsistent with the steady-state model's predictions, which led many researchers to favor models that allowed for a dynamic and evolving universe. Despite these challenges, the steady-state hypothesis contributed significantly to cosmological discussions and theories. It introduced the idea of a continuous creation of matter, which influenced later developments in cosmology. For instance, the concept of a dynamic universe, where matter is continuously created and destroyed, is echoed in some modern theories about the cyclic universe model. This model posits that the universe undergoes infinite cycles of expansion and contraction, which can be seen as a modern evolution of ideas initially explored by the steady-state hypothesis. Moreover, the steady-state hypothesis prompted further investigation into the nature of the universe and the fundamental principles of cosmology. Researchers had to consider alternative models and refine their understanding of cosmic phenomena. The competition between the steady-state and Big Bang theories drove advancements in observational techniques, such as more precise measurements of cosmic background radiation and better telescopic observations of distant galaxies. The debate also highlighted the importance of empirical evidence in validating scientific theories. The steady-state theory, despite its initial appeal, could not withstand the weight of accumulating observational data. This underscores a fundamental aspect of scientific inquiry. Theories must be adaptable to new evidence and continuously tested against observations. As cosmology progresses, the legacy of the steady-state hypothesis endures in the sense that it contributed to a broader and deeper understanding of the universe's nature. The hypothesis catalyzed discussions that led to more sophisticated models and theories, shaping the field of cosmology in significant ways. The exploration of cosmic phenomena and the quest to understand the universe's origins and evolution continue to be guided by the lessons learned from the steady-state theory. In conclusion, while the steady-state hypothesis may not hold the same prominence in contemporary cosmology as it once did, it played a crucial role in shaping our understanding of the universe. Its challenges to the Big Bang theory spurred significant advancements in observational and theoretical cosmology. The hypothesis remains a notable chapter in the history of science, illustrating the dynamic nature of scientific theories and the ongoing quest for knowledge about the cosmos. As new discoveries emerge and our understanding of the universe evolves, the contributions of past theories, including the steady-state hypothesis, will continue to inform and inspire future research in the field.